for you as I could. So okay, motor and motor controls. So Jeff, and nobody as a designer will ask you to grab your tools and go fix a controller or motor. They wouldn't ask you. You're not licensed, bonded, or insured in the state of Minnesota to do this type of work. You will be literally sued. Your company will be sued if they're an engineering company and they allow you to work and you went there and kill yourself. Everybody understand that one? So why do we care about controllers and motors then? Because we're the designers. Yesterday, you know what, Darren, I'm not kidding you. Yesterday, I had a contractor working on the Hiawatha, the light railroad, and he said when they were doing grounding, he was telling me about engineers who are asking to do physical grounding that has nothing to do with the code. And he said, and he's an engineer himself, the contractor is an engineer. He said, look what they're asking me to, this is completely out of whack. So they want him, he's bonding the track. And the track, when you bond the track, they want him to bring a sleeve to protect the bonding conductor, but metallic sleeve. And he told them, if you do metallic sleeve, then you have to bond it from both sides, as the code says. And how about if I put PVC schedule 80? That will solve the problem. Anyway, so the engineer insisted on using metallic sleeve. So he bonded it from one side, the other side is right under the ground. How are you going to bond it when it's on the ground? So long story short, the engineer wants him to bond both sides. So he ended up busting the concrete after they put the whole thing, bust the concrete, reach the other end of that sleeve and bond it to the other side. Now he's going to charge the engineers and get into all this argument versus it could have been solved with PVC Schedule 80. If you're good with wiring, PVC Schedule 80 is a great protection for your conductors for physical damage, especially grounding conductor. So my point is, why do designers need to know this stuff? Because you can be literally a half-ass designer if you don't know the code really good. I hate to use the term. Same thing for motor and motor controller. You're going to be in a situation where a contractor asks you what type of controller you want to specify for this motor. At least you should give him a couple of options, right? At least a couple of options, okay? So that's why we torture you guys with motors and motor controllers. So what we have guys about this chapter is going to be machine layout in the industrial building. It talks about all these machines that you see right here, all the machines that you see right here. These are old motors. So they take him and what type of motors are these machines on? So describe the various types of motor used in industrial building. The industrial building that we use right now, they talk about the type of motors that we use. The most common type of motor that we use is induction motor, three-phase induction motor. Everybody knows that one. But then we have a DC motor, and we have wound rotor motor. We'll say a few things about these. And of course, the single-phase induction motors. If you have a commercial building, typically we don't use a whole lot of them. Operation of the type of motors and motor controllers. Motor branch circuit and installation. We just remind you because we did branch circuits and feeders for motors. I am confident that all of you will be tested, by the way, on Friday on it. How to do branch circuits calculation on a disconnect, overconfliction device, fuses, overload, all this, as well as the feeder. So I'm confident that we cover these really good. Okay, machines and their applications. This is just a formula, guys, that they use, machines and their motors. Every machine in this manufacturing floor has some type of a motor that drives it, right? Some type of motor that drives it. So in order to find the full load current of any motor, any machine, this is a formula that they use, guys. You take the horsepower of that motor, multiplied by 746, divided by voltage, 1.73 efficiency power factor. This is, Jeff, this is called the full load current. That's how we find the full load current of a machine. Not an DC code book. Not an DC code book current. This is a full load current. So look at the power factor and the efficiency and the horsepower will be, I don't know if I can write. The power factor, doesn't allow me to write today. The power factor and efficiency and horsepower will be a decisive factor. In the size, I'm sorry, back here, in the size of in how much amp that machine is going to pull for you. Any comments, any questions, guys? We use this one to find the nameplate. 99% of the time, guys, the nameplate will be given to you by the manufacturer on the nameplate current on the nameplate. Motor types, there's a few things when you deal with motor control, guys, three symbols that you have to adhere to or look at. If you look at this is a symbol of relay, this is not new to you. We have a relays, transformers, diodes, and CSRs. These are the two things I would like to pay a little bit of attention to because that's what we use with soft start. We use them for soft start and VFDs. So I'm going to focus a little bit later on the soft start and VFDs. We have normally closed contacts, a bunch of resistors and circuit breakers, and this also armature. This is how the DC motor is represented. Overload uses normally open, push bind the stop and the stop right here. So all these and if the connections are in the schematics, if two lines are connected together, they put the dot. Can you see that? These are crossing lines, but they're connecting. Every time two lines connect each other in the schematics, they put two dots. So anyway, these are electrical symbols that comes very handy in page in your book, my friends. That will be page 130 that you probably must know. Okay, single speed squirrel cage induction motor. Single speed squirrel cage induction motor, guys, as easy as you can get. You have bars of typically steel bars shorted at the ends and rotating, that's the rotor, rotating inside bunch of coils connected as a single phase or a three phase. So copper aluminum bars run axially around the periphery of the motor. Good starting torque on them, and stator and rotor are linked by a common magnetic field. Here's what it looks like. Guys, you have the stator windings right here. You have your rotor bars, and you energize the rotor bars from these wires. You induce voltage into the rotor. When you induce voltage into the rotor, you create a current. The current creates a magnetic field. The magnetic field of the motor and the stator interact with each other to get you the spinning mechanism. Any comments, guys? Any questions? Any comments? Any questions? So here's, when you look at a motor, Brian, my friend, you have your shaft here. That's where you tie the machine to. You have the bearing, because the shaft has to rotate. You put bearings here. And then you have the stator force, the coils around it. That's where you energize the coil to create the magnetic field. And the rotor that captures the magnetic energy. When I was your age, Adam, it confused the crap out of me. How on earth can you convert electricity into motion? Right? You're converting. This is a converter. A motor, guys, is an electrical energy to mechanical energy converter. Right? Converts electrical energy to mechanical energy through the electromagnetism. So it's really cool. Very simple. You create a magnetic field here, north and south. It induces another magnetic field in the rotor, north and south. You put north next to a north, what happens? North pole next to north pole, they pull away each other. And because of the AC rotates, you create a rotating magnetic field. So the north keeps rotating in the stator, and the rotor keeps chasing the rotor north, keeps chasing the stator north, and that's how you get yourself the spinning mechanism. So that's, if somebody asks you how it works, I know you guys we have touched on that one before, but the most important thing is, here's your J-box. You're not going to be wiring. Of course, that's where you bring your conduit, typically flex, to tie to it. Any comments, guys, about the basic construction of an induction motor? Basic chunk of metal rotating inside a coil. What is a coil? A wire that's looped. That's what a coil is. Okay, so that's basically it in terms of single-speed induction motor. So that's the magic behind it. Is you induce the voltage into the rotor, you create the magnetic field of the rotor, the magnetic field of the rotor and the stator interact with each other to rotate. One of the most important formulas that the mechanical engineer is going to be asking you for, guys, one of the most important formulas mechanical engineers will be using is this formula. This is the torque. To torque, what's the torque? The torque is a twisting force. So from a mechanical engineering point of view, I don't care what your horsepower is. I don't care how many amps coming to your building. Give me my torque, right? Why? What do you do with the torque? You make things spin at a certain force, right? So that's one of the most important things. The way we find the torque is we take the horsepower that you designed the motor for, multiply by this magic number 5252, and divided by the RPM of the motor, the RPM of the motor. Can you guys see what happens if you slow your motor? The speed is lower, the torque goes higher. Can you see that? major advantage in terms of torque. If you spin it at a higher speed, the torque goes what? Lower. So there's a relationship between the torque and the speed. As the torque goes up, as the speed goes up, the torque goes down. And there's some adjustment with the VFDs for them. Any comment, guys, about this formula? T stands for the torque, the twisting force, horsepower, multiplied by the magic number 5252 divided by RPM. Who cares about this formula? And why didn't we use it in any of our applications when we size? We use it, guys, in our electrician program. You guys have used it. We have tons of calculation in our motor lab. When I was teaching motors, we spent a week on calculating all these efficiency and all this stuff. We're designers. The only thing you need to worry about right now is just the torque. Give this one to the mechanical so they can get their torque. Okay, here's the induction motors in the industrial plant that we have. Numbers. MA is engine lift. See this one? Length. Okay. 20 of them. Number of motors is 20, as well as the horsepower of each motor is 5. So this is a list of all the machines that they have, guys. And where are these machines, Jeff? They're right here. See that? These machines are fed from the bus stop. Okay, so we have shapers here, 6 shapers, 6 motors. So multiple motors, multiple machines, and the horsepower of all of them are single-speed squirrel cage motors. Single-speed squirrel cage motor and induction motors. So this is just a list of all the machines that we use in this plant. Number of motors, description of a motor, 6, 3 horsepower motor, driving 6, ventilating. So these are kind of a bunch of description of the motors that they have. They have 23 motors, half horsepower motor used as 23 machines equipped with oil, fog, precipitation units. So what I'm getting into, guys, is you walk into a manufacturing floor, and that's what you get from the manufacturing engineers. A list like this and say, power this equipment for me. Power this equipment for me. Any comments, any questions? So I care less what these are doing. Do I? I really don't. I don't care what they go. Here's what I care as an engineer. How many of them and what's the horsepower? Then I design my bus stock. Here you can see when I design my bus stock here to feed all these machines. Any comments, guys, about this? Any comments, any questions? The reason why this is important, Aaron, because you guys have a list of machines in your project. Not this week. Next week, you're going to be doing power layout. What do you need to do? You're going to grab all these, size the bus stock like we did, and so that's the size of the bus stock, 400 amp. Then I need to size a disconnect, a fuse disconnect, and an SO cord to feed these machines. Okay? So what do you need to do that? You need the horsepower of the equipment, and the voltage, of course. Any comments, guys, about this? Any comments, Aaron, my friend? So that ties directly to the project that we have in terms of sizing the equipment for it. Okay, 4-speed squirrel cage motors. So most of the motors, guys, are single speed. And if I want to have multiple speed from him in this day and age, what they do is they put a VFD on it. VFD can speed that motor and actually to a synchronous speed or even higher. So each of the 2 windings can produce total 4 speeds. Speed are obtained by changing the numbers. So what they have, guys, you can have induction motor 1 speed, and then you can have induction motor multiple speeds. The way they do the induction motor multiple speeds is they have multiple windings. By energizing winding number 1, you get 2 speeds. By energizing multiple winding number 2, you get another 2 speeds, or vice versa. So by energizing different windings, you can get different speeds. Okay, so let me show you for this one. We have a couple of induction. We got that one. Okay, so here's my induction motor. Here's the rotating magnetic field, north and south. Start motor. Okay, here's a multi-speed motor. Here's what they do with multi-speed motor. I don't know, anybody have seen them? When you go to multi-speed motors, they're designed to run at different speeds, 4 speeds. So they can go forward and reverse. You can have this one, 1, 2, 3, 4, 5, almost 5 speeds or 4 speeds. But you can reverse. In reverse, you can go 600. So here's how you can get by sliding this arm. By sliding this arm, guys, you connect and disconnect certain coils. I'm not going to get into the details which coils, and then you basically alter the number of poles, and when you alter the number of poles, you alter the speed of the motor. You alter the speed of the motor. Any comments, any questions? Um, this has been solved therein by one little thing, VFD. In order to have this, but this has to be a special motor that runs at 4 speeds, and you can see the speeds are half of each other, right? So you have, let's say here 600, 900, 1200, and what's the other one? 1800? 1800. And only steps. I can solve the problem instead of this type of a motor now with a VFD, with my VFD. Okay, so I'm going to show you that one anyway before we get into that. Any question, guys, about the 4-speed squirrel cage motors? They design them with 2 sets of windings. You energize one set, you get 2 sets of speed. You energize another set, you get another set of speeds. That's basically it. When it comes to induction motor, guys, the problem when it comes to any motor, you have 3 things you need to worry about when any motor, you put any machine online. Number 1, starting torque. The starting torque and the starting current. If the starting current is so high, you can kill the electrical system, dim the whole system. That's a starting current. We need to reduce it. The other one, guys, the starting and stopping the motor or reversing it, that's another thing you need to worry about. And speed control. You need to be able to speed control the motor. So, Jeff, my friend, here's how they do resistance starting motor. Guess what they do? They take a resistor, they put it in series with the motor. When they energize the motor, the voltage here is 480, but the voltage across the motor for 10 seconds will drop to 240, right? So they lower the voltage momentarily, the inrush goes down, everybody's happy for only 10 seconds. After 10 seconds, bam, they slam these contacts here, shot, bam, 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 all these shots. They shut these resistors and the motor is running at full speed. Long story short, this is called primary resistance starter, guys. You still use them in the industry. We still use them in the industry. There's bank of resistors. The ones who were with us, guys, if you were with Gary, I don't know if you wired some of them, but our students right now, they wire them in the lab with resistor. They put the resistor in series. Can you guys see that? 480, knock it down to 240 for 10 seconds. The starting current goes down. I don't dim my lights when I start my motor. After 10 seconds, the control system, the timer times out. This will close. Bam, bam, bam. You shunt these resistors. You basically have a path around it, and you have full speed across your motor, and your motor is up and running. Your motor is up and running. So that's your starting. That's voltage reduction. Now, Kerry, when you size when we guys were using SKM, remember when we used SKM and we used the Cummins generator software, they always ask you across the line start. Do you have across the line start? Across the line start? Or voltage reduction start? You're looking at a voltage reduction start. What you're looking at right here is voltage reduction start. These are voltage reduction. You reduce the voltage. With resistor, here you reduce the voltage, guys, with the auto transformer. So you bring 480 here, you transfer it down into 24. The motor starts slowly, gently, come up to speed within 10 seconds. Bam! You shunt the auto transformer out of the picture. Means you close the contacts across it, and your motor is running at full speed. Any comments? Here's what I want you guys to know without getting to the details. I want you to understand there are 3 ways of speed controlling a motor. Number 1 is across the line. This is just magnetic starter, slam shot, and it's running. The other one, you reduce the voltage to reduce the inrush and the torque. The other one is speed controlling, which is also you reduce the voltage and the frequency to reduce the inrush and the torque, as well as speed controlling. Any comment, guys, about voltage reduction? The only thing I want you to understand, when you go to comments and they ask you what's the controller on this motor, they're going to be talking about voltage reduction. Here's the voltage reduction. You take 480 to a transformer, you reduce it to 240, start your motor, only for 10 seconds. After 10 seconds, you shunt the transformer out and the system is running at 480. Any comments, any questions, guys, about this auto transformer? Aaron, does it make sense? You put the voltage here, You close these, the start. Now you're getting all the 480, and then the timer times out. It closes this one. When you close it, the R1 to R shot close. Basically, it's like putting a wire around across the transistor. Well, you need to do the control in terms of, you don't need another one. You only trying to isolate, when you isolate the system, when you go here, 1, 2, 3, and you close them, you really brought the power directly into the motor. You isolate. Then you don't need for another contact to isolate. You could. So these are two, when they close, they energize this. This will continue to energize. So when we have the timer times out, here's my timer times out, this will isolate 1, 2, 3. Now this will continue to have some power. I see your point. This one continue to have some juice up to this. So if you want to fully isolate it, you probably need another contact right in here. Another contact. Does ours in the book has that? No, they all have. I see your point. This could be a safety hazard, guys, Jeff, right? Because when you close it, you still have some power right at the auto transformer. But it's not going anywhere, though. It's just sitting there. Other than safety hazard, the system will work perfectly. If you want your auto transformer to go completely isolated, you have to put another contact right in here. Absolutely. Here's how it goes, Aaron. Your voltage, full voltage is 480, right? For 10 seconds, it dumps it down through the transformer to 240. The motor starts. The torque is low, so I don't bust the machines when I give big push to the machines and bust them, number one. And I don't dim the light when I start. That's the advantage of reducing the voltage. For 10 seconds. After 10 seconds, my motor slowly, gently starts. And you know what they do after that? They raise the voltage back to the regular voltage so the motor can give you the full horsepower and the full torque. The only thing you need is probably for safety, because right now, if you leave it as is, when this is energized, there will be a voltage sitting right here. But this is inside the controller. There's tons of voltages anyway. Yeah, it's not needed for the control system, but from a safety point of view, probably. But if it's inside the controller, you open the controller and the motor is running, you're exposed to a lot of hot stuff. Any comments, guys? Any questions? Any comments? Any questions about the reduced voltage start, as they call it? There are three ways: either resistor in series, or coil in series, or auto transformer. The ultimate solution, guys, reduce the voltage, start the motor gently. Then when the motor up and running, raise the voltage so you can get the full potential, horsepower and torque out of your motor. Okay, so that's for induction motor. The other motors, guys, wound rotor motor. Wound rotor induction motor. These guys, they have the rotor itself have some coils inside it. That's it. That's the only difference. Coils inside it. So you have to have brushes and so forth. The advantage of this one, Jeff, the wound rotor motor, they have huge torque. They are really good horses. So if you have bunching, breast bunching, like bunch bracing and so forth, they need a lot of torque to make holes. They use a wound rotor induction motor. Sam, how does it work? It works in the same principle, guys, as induction motor. Okay, so the secondary resistor, except they have a secondary resistor, I'll show you. Press motor can be operated in any of the three speeds, so you can have a full torque out of it, reduce the torque, so you can control the torque of that motor. That's the only reason why we have the windings in the secondary. Here's an example of that one. I don't think we have the, before I take you guys over here. Okay, so we got that one, starting torque, the coil. Okay, here's your wound rotor induction motor. Here's the stator, guys. Here's the motor. If you go into a motor and you have coils coming out of the rotor and have bank of resistors, the more resistors you put, the slower the motor will be. And when you want to shunt all these resistors together, close one, two, these two, when you close them, the motor will run as an induction motor. So when you start your motor, guys, all these resistors are in the circuit, so it starts slowly, gently with good torque. And then when it's up and running, you shunt these to get you to control your torque. Low speed, second speed operation, third or high speed operation. So depending on how you, the low speed, you put all the resistors in. Second speed, you shunt at B. Third speed, the high speed, you shunt at C. So that's your speed control for these motors. Wound rotor induction motor. Any comments, any questions with the advantage, guys, of VFD right now? Well, they still have some application for torque, but VFDs took the place of a lot of these motors, unless you really, really need a torque on them. Any comments, any questions about this type of motor, wound rotor motor? You can see that there's, if it's an induction motor, everything from here to the other side wouldn't even exist. Just chunk of coils. There's so much about motors, guys, that you can even imagine. So that's what here's how it looks like with the controller, my friends. When you start the first speed, you connect. This is the first speed. This is second speed. Close these two. Third speed, which is the high speed, close these two. So they control the current in the rotor by closing contacts. And I'm not going to go walk you guys through all this control system. You can walk it. But if you're a control engineer, that's where you go. It's really not hard for second speed and fourth speed and so forth. So speed control of these machines. Any comments, any questions about wound rotor motor? Where would we use it? Speed control is number one, and you need torque. Can I use this one in air handling unit? Yes. Is it good application? No. For machines, the challenge, guys, for machines therein, we don't even specify the motor on the machine. It comes by the manufacturer. Just be aware of it. I've never been in a place where I have to specify a wound rotor motor. I mean, it usually becomes part of the machine. But be aware that there is something called wound rotor motor, and that's how they work. Any comments, any questions, guys? Any comments, any questions? So that's basically the type of the motor. I'm going to take you back into here. So we have induction motor. We have the secondary conductors. This talks about, so that's it. So we have an induction motor, wound rotor motor. I'll talk about the DC in a second. This one talks about this. This is for you. You're a project manager. You walk into the building and you need to connect a motor to a system. Well, if you flip two phases, what happened to the machine? Instead of exhausting air out, start pulling air in because you change the rotation. So that's when the hand becomes, guys, rotation determination is a big deal. This is how this works. This is the phase rotation machine. You connect it to the machine and you spin the motor. If the motor goes in the direction that you want it to go forward, right? So you tie phase A, B, and C here and spin the rotor. It gives you an indication that's correct. Then you will disconnect them, tie them to the line, and with the hot line, it should spin in the same direction. If it doesn't, then you just change any two phases. So correcting the phase rotation meter to the motor. If you're a project manager, again, we don't use this. That's as designer, guys. But be aware that before you connect the machine to a line, you need to make sure that phase A, phase B, phase C is lining up. If you flip them there, what happened? You rotate the machine. It's going in the opposite direction. Bad news. So that's why they have this rotating machine, phase rotation, that identify the rotation of the equipment. Be aware of that. Okay, connecting dual voltage three-phase motor. You guys have done that one, and this is just FYI only. The only thing I want to say is, if you have a delta motor, it comes in 3 pieces. Each piece, can you guys see here, 3 pieces? 1, 2, 3. Each piece has 3 wires coming out of it. If you have a Y motor, it comes in 4 pieces. 1 piece has 3 wires coming out of it, and another 2 pieces or coils have 2 wires coming out of it. And we label them from clockwise from the top of every coil, as you can see, all the way until you get them all that label. And I'm not going to do too much on that one. Okay, dual voltage single phase motors. If you have a single phase motor, guys, dual voltage, Almost all motors are dual voltage because it gives you two voltages to run your equipment on, voltage 1, voltage 2. We have split phase. Could be both running and starting windings. You can run them at high voltage or low voltage. Low voltage are in parallel. Let me, I don't know if I have an induction picture of that one, very easy. Okay, so let's go here. We got that one. So here's how the rotation is, guys. Here's my motor. Tie it to the motor. Make sure you spin the rotor. Gives you one indication, correct indication. Go connect it to the line. And then when you connect it to the line, give you the same direction. Okay. If it's not, you just flip any two phases. Any two phases. Okay, you can also connect it, Jeff, to test if you want to tie two systems together. Two systems together. You go to the existing building, and that will be your phase A, B, and C, and then you go to the new system. It should, if it shows A, B, and C correct. If it doesn't say correct, then all what you have to do is just go flip two phases. So you don't want to. You have to check the phase rotation. Absolutely. So that's you're going to go first to the existing, identify A, B, and C, and then you're going to go to the temporary, identify A, B, and C. If it doesn't give you correct when you flip them, all what you have to do is just make A, B, and B 8 and done. Flip any two phases. Right here. Oops. Let me go back. Now if okay, back here. Okay. So now you're going to tie. Here's your A, B, C. A, B, C, right? You're going to tie these two together. Here's my three, tie them together. Cool? Now, if it gives you correct when you tie them, you tie them this way. If it doesn't give correct, look what you do. You go this way and you tie them this way. Yeah. You tie it to the system this way instead of tying them what? This way. Any two phases. Do you see that? That's really good. Remember, you flip any two-phase and three-phase system, what happens to the rotation of the equipment? Reverses it. That's kind of the drawback of the three-phase system. We talked about gas windings and connection. You can connect your equipment if you put the coils in series, you get to high voltage. If you put the coils in parallel, here's a parallel coil. This is low voltage. Here's the series coil, high voltage. And you guys will read that one. Here's parallel coil, low voltage. Low voltage again. So we're paralleling the coils. Every time you parallel the coils, you get your low voltage. Okay, when it comes to single phase motor, guys, they come in three pieces like this. If you put the coils in series, you get your, here's in series, this is high voltage. Everybody can see that. If you want to put them in parallel like this is a low voltage. High voltage, low voltage. High voltage, low voltage. Any comments, any questions about that? High voltage, low voltage, and I know this is shouldn't be new material for you guys. We always have the starting windings and the running windings. The starting running windings. The starting windings typically, guys, they have a centrifugal switch that at a speed of 75% of a motor, it flips it and isolates the motor. Any comments about split phase induction motor? Split phase induction motor. Oops, close that one. Okay, so we got that one. Now, if you have one start winding here, this is how you connect them, starting winding, guys. This is high voltage, this is low voltage. High voltage, low voltage. High voltage, low voltage. Any comments, any questions about them? Look at the labels, T1, 2, 3, 4, 5, 8. 1, 2, 3, 4 is for the running. 5 and 8 are always for the start. And I run right through this one, guys, because you're not an electrician. We spend a whole semester teaching motors. You took the motor with us, right? We spend a lot of time on these. This is for you guys are the a lot of flashback memories. Okay, so that's basically the my split phase induction motor. Okay, let's go to. I got my split phase induction motor. DC motor, guys. Then, so that's my induction and wound rotor motor, single phase and three phase. DC current motor, DC motors are great for speed control. That's the advantage. Speed control are horses for them. So if you have a DC motor, what they do, guys, is they run them at DC, right? Through brush rings and commutators and so forth. They run them at DC, and they get you a good torque and great speed control. Every time you tweak the voltage down, guess what? The speed goes down. That's why they were superior at one time, the DC motor, because speed control. Now, with the advantage of the AC system, with the VFDs, their advantage is not a whole lot. Here's a DC motor, guys. The armature here, there's coil inside it, there's brushes at the end. You tie your conductor, here's your coil, a series coil, and shunt field coil, and you tie them in this way. It's called short shunt connection, long shunt connection. I always wondered, Aaron, who cares? Long and short and so forth. They can give you guys, the whole idea of motors is to give you speed control and torque. Which one can give you high torque and which one can give you speed control? So they do all these connections without getting into too much details for you. And based on certain connection, give you great torque, great control speed. Others get you better torque, better control speed. So they keep connecting in different ways to control the speed and the torque of a motor. Speed of a torque of a motor. Here's another connection for cumulative and differential compound connection motors. Here's the field. There's series field, shunt field, armature, and commutating field, guys, for these. Be aware. I mean, without getting into the details, here's how you get them, Jeff. How do you wire them is based on, is it going to be a cumulative or differential compound? Who cares? What cares, guys, is the torque and the speed will decide what type of connection you will have for this machine. Typically, these are connected before we even walk into the place, guys. So we take a DC. That's why I don't spend too much into the details of them, because you're not an electrician. If you're going to troubleshoot the system, then a whole different story. A whole different story. Okay, series connection, parallel connection, clockwise. How to rotate them? Shunt motor. This is going to be in the test. How to rotate them? If you look, guys, here's A1, A2, the armature field is F1, F2. Now hit you clockwise. Look how counterclockwise. See what they did here, Aaron? They run A2, A1. They flip them. They just flip them here. How do we flip them? Instead of connecting this wire to this wire, I just flip them. I connect them this way across the armature. That's how they rotate a DC motor. A DC motor. How do they rotate an AC motor single phase, guys? They change the starting coil. Flip the starting coil. Any comments about the DC motors connections, at least reversing them, Adam? The only thing for reversing, you can see that A1 and A2 here flipped. That's how you reverse it. We got that one, same thing. You always look at A1 and A2. Can you guys see how it's flipped? A1 and A2. Same thing for the compound. Okay, so that's what I'm going to do for these one. The second thing, guys, if you have a DC motor, you need a DC source of power. How do you get DC source of power? Everything that we generate right now is AC. How do you get a DC source of power? You need to have a converter, right? You have to convert. So what they do is, Jeff is a DC motor, and I need to power it. That's important for us. So you walk into a building, and they have multiple DC motors. The first thing comes to your mind is, how am I going to get DC source for them? No problem. You need a converter. So you will start the starter for this machine must have a converter. That's all we do. So you bring three-phase to the converter, convert it back into DC, and dump it across the motor. So we have simple halfway rectifiers. So converters, guys, rectifiers. If you remember, we have diodes. Every time you put a current to a diode, it cuts one half of it. So we have the forward bias and reverse bias for diodes. And I'm going to take you directly into the electronics. Here's what they call it. In order to get your AC, DC to your DC motors, you need a converter. Your converter is nothing other than diodes like these. So you put the AC into it, and this side becomes half of an AC, basically, which is some form of an AC, right? Then the smarter than Chad go and have a three-phase. Look at this three-phase, guys. This is a three-phase. Draw on that one. Here's a controller that you guys are going to order for your DC motor. Here's my AC coming in. Here's my controller, converter basically, and this will convert it into a DC. And you can see the top. This is what my DC is. That little bit rebel here. So, long story short, as far as we're concerned, Adam, my friend, when you have a DC motor, the first thing must come to your mind is, I need a DC drive. Do you hear the word DC drive? Right? I need a DC drive. What does a DC drive do for living? It takes 480 and convert it into an appropriate DC level, dump it across the motor. Done. Without getting into the electronics and how it converts and inverts and so forth. Any comments, guys? Any questions about this? So here's my single. You wouldn't see this one a whole lot, but you would see this definitely, the three-phase one. Okay, so what does it do, guys? It takes the arm mass, which is 1.4 times the peak, and multiply the peak by 0.63, and that's how we get you the average value multiplied by 0.6 for a full rectification. So this is just to get you the value, the voltage value, the DC voltage value. If it's half, you divide it by 2. So if I have a 480 system therein, you multiply your 480 by 1.4, you get you the peak. Then you multiply it by 0.637, I will get you the DC. Piece of cake. If it was a single phase rectification, which highly unlikely you're going to use in 3 phase, you divide the whole number by 1, 2. So typically we don't get involved in that one. This is FYI only as a knowledge. But when you have a DC motor, you specify a DC drive, and the DC drive will drive the voltage appropriately to this DC motor. So you walk into a manufacturing plant and they tell you we have DC motors, the first thing comes to your mind, I need to specify DC drives. Okay? Not not speed drives. They are speed drive, but not frequency drives. Frequency are AC drives. You need a DC drive. Can I have thumbs up, chat, the DC drive for these? Okay, so got that one. Here's the rectification. There's different technologies that they can use, guys, and I'm not going to get you. You're going to see SCRs. The SCRs is one of the technologies that they use to rectify versus diodes. And here's all the controllers in the first shift. And ultimately, when you have a drive, guys, ultimately, the DC drive takes the AC, convert it to DC, and allow you to tweak the DC so you can control the speed of the motor. That's ultimately what you do. So I can, if you slip through all of what I said, guys, one thing you have to wake up and remember. If you have a DC motor, you're specifying a DC drive. What does a DC drive do? It takes AC, convert it to DC, and it alters the DC to speed control the motor. Done. Is that simple? How does it do that, and what's the magic? Diodes and SCRs, you can read them on your own. Any comments, guys? Any questions? Any comments, any questions about the one? So that's what I want to drive directly to you. DC drive motors, less expensive compared to DC drives and DC motors. Now VFD. Now we're going to the VFD. VFD. Speed not as controllable, less expensive, less downtime. Now, instead of having DC motors, guys, and DC drives, here's one solution. The other solution is to have AC motors and AC drives. These are your VFDs. Can I drive, guys, DC motors, DC drives? Then you have AC motors and AC drives. The AC drives are called VFDs. Okay. The advantage of VFDs, guys, are you don't have to deal with DC motors. That's high maintenance and less downtime. So they have a lot of advantage because you can put them in an induction motor. An induction motor, guys, is the least maintenance, less maintenance. Okay. So the principle of operation now we went from the DC drive to the AC drive. AC drive, the principle of operation for these boys, it reduces the voltage carry. His voltage went from here to here, and at the same time, the frequency it goes from here to here. So they alter the voltage and the frequency. By altering the voltage and the frequency, guys, they will control the speed of the motor. So they take a motor, the AC, and they start altering the frequency and the voltage here, and dumping it across the motor at different frequency of voltage. By altering the frequency and the voltage, they can speed control the motor. And that's exactly what I love. They can run it forward, reverse, at almost any speed I want between synchronous speed and 15 RPM or 30 RPM. So that's your voltage conservation. So that's where it talks about the voltage conservation for them. So in order to reduce the voltage, if you reduce the voltage in AC motor, you burn it. But and why do you burn it? Because if you reduce the voltage and keep the frequency the same, guys, you have more current going right through it, right? So we reduce the voltage, they burn the motor. In order not to burn your motor, we reduce the voltage, and proportionally they reduce the frequency, on the motor and the voltage. So that's how do they do that? Here's the magic. That's what you guys all care about. Here's the magic. Take this. You take an AC, you convert it to DC first, or some form of a DC. You alter it, change it, and then you make sure that these transistors fire at different times and at different values. All electronic drive, AC drive. That's your frequency drive. When you see an AC drive, a frequency speed control, you take whatever AC you have, single or three-phase, by the way, and look at that. I took single phase and I converted it to what? Three-phase. I can drive a three-phase motor from a single-phase system using a VFD. That's one of the advantages. So long story short, you take the AC, convert it to DC, smooth it with a capacitor. Then, with these transistors, they control them, and transistor does nothing but a switch. They make them open and close at different magnitude and different interval. So when you're done with this, I think we have, when you open them and close them, guys, you get yourself an some type of a step voltage that looks like AC, which speed control the motor. So you can use SCR. So this is just this is some of the advantage of SCRs, guys. The harmonics. Remember the harmonic that we talked about? Overheating transformers and motors, blow fuses, transistor driven into saturation. So they have two technologies: SCRs or IGBTs. These are the technologies that you use. If you don't want to get into the details, order IGBTs. IGBTs, these are transistors. Insulated gate bipolar transistors. Did you guys do electronics with us? Some of you? You did some electronics? Yeah. Voltage control devices, ability to turn on off. So they use them, guys, to convert and invert the voltage. So they have they're superior to the SCRs, basically. SCRs. Advantages: SCRs not used in power supply, reduces problem with line currents. Disadvantages: rate of transistor can cause voltage spikes. So their advantage over SCRs, guys, is their problem is, look at that, because they flip so fast, they can have a pulse 1600 volts. So it creates transient issues in your system that you have to deal with. IGBTs. Any comment, guys, about the IGBTs, SCRs? Let me just give you, before we go there, let me show you a couple of pictures. That's all. I know it's Monday. I don't want to overwhelm you more than, okay, we talked about these. Okay, here's how the diode works, guys. It takes the AC, cut it into half, then double. Then you have, they have the bridge, two diode or a bridge. It takes you into a smoother AC. Then the best one, Jeff, my friend, the best one here is, of course, is this one. Can you guys see that? It's almost constant DC. Almost constant DC getting in here. That's how you get the AC 3-phase 480 into this value. Here's a much better one when you bring a 3-phase. Look at that. Don't you guys think that this is as close to a DC as you can get? This is as close to a DC as you can get, right? Dumping it right across this DC motor. So anyway, so that's your 3-phase bridge rectifier. They call it 3-phase bridge rectifier. That's your DC drive. That's what your DC drive does for a living. Okay, then you get into the phase shift controller to control it. And I want to go into diodes and transistors. So we got that one to shift them. We got that. Okay, so I want to go directly into this one, guys. Okay, here's Jeff, my friend. Here's how your VFD works. You got your AC here, converted to DC. So your voltage, guys, here looks like this. When you invert it here, it looks like this. Then you invert it at this side, and it will look something like this. Does that make sense? That's what the whole magic about the using CSR control output voltages. So you use your diodes, you convert to DC, and you invert it back to AC. By converting to DC, guys, you can control how the magnitude of all these transistors here, how they fire, the magnitude as well as the time for firing them. And who cares? At the end, there, my friend, here's what you get the voltage coming out of it. It's a square voltage that your motor likes. It's okay, and it controls the speed of the motor, controlling the speed of the motor. Okay, so that's guys the outcome of this. Here's the signal that's coming out of outcome of an inverter. Here's the IGBTs, the outcome of an IGBT. It's smoother. Where did it go? Here you go. That's why IGBTs are better, guys. The technology, it gives you smoother, better control. The signal will look something like this. Any comments? Any questions? Summarize. If you have an AC, a DC motor, you specify a DC drive, so you can control the speed and feed the motor. If you have an AC motor, induction motor, you specify an AC drive, which is called VFD, and technologies, IGBTs are the most superior right now. That's all just FYI, IGBTs, you take the AC, convert it to DC, invert it back at the right frequency and the right speed, and by altering the frequency and the voltage, you get yourself different speeds. Really, that's what that's an outcome of a VFD, guys. Look at the pulsation. As far as the motor concerned, as far as your motor concerned, this is nothing but an AC signal. Your motor will be cheated to think. Your motor will be cheated to think that this is an AC signal. Does that make sense? So that's basically that's the best technology that you can use, which is this IGBTs. Okay, so that's then Jeff, because of all this, so everybody in school with IGBT technology in VFDs, everybody's cool with an AC drive, which is the frequency drives, and DC drives, which is to drive the DC motors. That's really what we're going to do. The last thing, guys, in my thing here to do is almost done here. So we got these, we talked about IGBTs. Then, you guys remember that signal, the pulsation signal? This is so harsh on the motors, so harsh. It creates a lot of heat in the motors. So the manufacturer of the motors start creating something called inverter-rated motors. Therein, you're going to hear this all the time. When you're an engineering firm and you go to the air handling unit, rooftop unit, when you read the specification by the mechanical engineers, they will say the manufacturer must provide an inverter-rated motors. Now, what the heck is an inverter-rated motors? It's a specially designed motor, same like an induction motor, specially designed, more robust, fat, fluffy, that can handle the heat generated by driving it with a VFD. That's all. So remember that one. So what does it do for living? It has separate flow to provide continuous cooling for the motor regardless of the speed. So it cools the motor, has some mechanism of cooling the motor because it gets hot. We have insulating paper, more insulating paper, guys, right here. It has more insulation between the windings and the stator core, phase paper added to the terminals, magnetic wires in a better quality, more insulation, case is larger. So as far as you're concerned, guys, it's better built motor to handle the stress that VFD can create on an induction motor. Sound good?
So the VFD is operating at the same current and the same horsepower, it's going to cause more heat.
Yes, not at the same power, the same horsepower. When you reduce the voltage, and you in turn you reduce the frequency, and there's some of them that maintain the torque, others they actually reduce the torque too, control the torque. That altering, instead of just letting the motor run at whatever horsepower is designed for and whatever speed is designed for and whatever torque, right? That will allow the motor to run based on its rating. Now we start altering the torque, the voltage, the frequency, and the current. it creates stress in the motor, in the form of insulation and in the form of spikes, voltage spikes. So if you insulate the system better, you can handle the spikes in the voltage, meaning you're not going to damage the insulation and short. So the only thing I want you guys to remember, very important, Adam, being designers, is when you specify a motor, most likely you don't, but you're going to see it on the mechanical engineering spec. Inverter rated motors, so it can be driven peacefully by an inverter, a VFD. And oh, by the way, Zach, they are fat and fluffy. They're large. The inverter motors, for the same size, they're bigger. Anybody knows why bigger? They put more insulation between the windings. Okay. So this is your VFD, guys. Drives using SCRs and GTOs. There's another GTOs. These are different technologies that you can use to convert with all the ins and outs. We're not going to get into them. Features of VFDs. What do you do for living VFDs? Low speed torque. So here's what the VFD is. I hate to say it, but one of the best that you can get in any machine, Jeff. It takes your motor, its speed, its ramp your motor up, meaning the torque, and the current is low, no stress, mechanical, electrical stress in your system, and it makes it run at this speed. Then when you want to turn it off, it ramps it down, so it also reduce the mechanical and electrical stress on the machines and electrical equipment. So these two guys are soft start, called soft start. But the VFD also can speed control the motor. For reverse, forward, speed control, ramp up, ramp down, as best as you can get in terms of a motor. I can ramp my motor up. When I will shut it down, I can ramp it down. And when it's running at full speed, guys, I can also speed control it. Running at 500 RPM, 1800 RPM, 200 RPM. You know what I mean? So isn't that cool? If you have a conveyor and you can control the speed now, instead of the things are all over, you can run it as slow or as fast as you want. Big deal. Big deal in the machine and manufacturing industry, guys. Big revolution. One all the time. One advantage, guys, also is you can take a DC system in your basement. You can take a DC system and feed a three-phase motor, though you have to derate, some derating happening here. But you can, if you're a farmer and you have a conveyor and you don't have a three-phase system, buy a VFD, tie it to the three-phase motor that you bought, tie it to your system, and derate it, typically 80% of its rating. You can't run a 15 horsepower at 15 horsepower. You have to derate it a little bit less. Basically, put a less load on them, and you're good to go. AC, single phase, driving three-phase motor via VFD. Okay, so what do? You can change unit program. You can current limit that. In rush current, you can limit it. Both your hertz, maximum, minimum hertz. So you can set your maximum speed for the conveyor, the minimum speed, your current limit. No matter what, don't want to exceed this current because that will interfere with the operation of the electrical system. Torque, you can control the torque on some of these. So it's really, depending what you have, is really cool system to have. Any comments, guys? Any questions about this chapter? Zach, do me a favor, really, will you? So that's really, I know some of it, guys, is FYI only being designers, but the last thing you want to do, you be a designer sitting there and they're talking about inverter motor and you have no clue what they're talking about. Or DC drive or AC drive, at least know the lingo that they use. Knowing how these drives work is great. I mean, you can read through them. There's people who are specialized in designing them, guys. My job and yours is to understand how they work and how to apply them. That's really our work. So let me see if I left anything on my pictures here. Okay, so here's a couple of converters, and there's a couple of VFDs, guys. Motor efficiency and power factor. I like this picture, guys. This is one of the things that I like about motors, because let me delete that one. See if I can delete it. Because it provides you. Let me move this one to the side. This give you look at this a quarter horsepower at. If you can see, guys, the best operation for a motor is it's full speed, 3/4 load, full load. Can I get you guys to look at this one in this way? If you want your motor to be efficient, and the power factor to be the best, you have to make your motor run at full speed. Unless you have VFD, of course. Unless you have VFD, you have, if you run it at half speed, half load, look at how it's screwed up. So for example, here's my efficiency 60, 67, 69 at full speed, power factor 45, 56, 65. So the efficiency and the power factor, guys, go up as the motor reaches its full speed. That's all what you need to do about that one. Okay, we talked about the machines, frequencies. Okay, and that's basically all we have for you. Any comments, guys? Any questions about this chapter? Really, I want to emphasize some of it. A lot of it is review. The only thing I would like you guys to pay a little bit attention to is AC drives, DC drives, inverter motors. These are, we get involved in it all the time. You need to understand that if you have a DC motor, you need a DC source, that's DC drive. If you have an AC motor, your option is to have VFD, which is called AC drive. So that's basically, and the technology that we have. The more you know, as I said, the better you will be as a designer. If you are an electrician, you're going to get into changing the brushes, and cleaning the commutators, and a couple of other things that we get into. Any comments, my friends? Any questions for Chad? Mechanical engineers. This has been the debate for years. Do you know how the air handling unit is going to work? Do you know how you speed control it? Well, I know how it works. Do you know how you want it to work? So almost all the mechanical equipment, guys, the control on the mechanical equipment, very good point, are picked by the mechanical engineers. What? Well, how do you think the mechanical engineers pick it? Recommendation from the manufacturer. Like us, guys. So almost all the, because where do we use VFDs and drives? On machines. Who specified the machines? I don't put an air handling unit in a building. I power it and sometimes control it, and most of the time a different contractor actually does the control. So yes, it's driven by the mechanical engineers. Any comments, guys? Any questions? Any comments? Jeff, does it make sense, my friend? You heard it for the fourth time now? Yeah. The only thing I want to say is to say inverter motor, AC drive, DC drive. These are really the bring home. The rest of it is good information. Cool? That's all I have for you guys. Thank you.